Great. So our next speaker is Adam Levine from MIT, and he's going to tell us about the non-perturbative Hilbert space of JT gravity. Adam.
Thanks. Yeah, thanks for the invitation to speak. I'll be talking about this work that came out earlier this year with these authors, and at the end, if time permits, I'll touch on some upcoming work with Luca Iliescu. Yeah, so I wanted to start with a, oh, this is not working now. Sorry. Nice, cool. Yeah, so I wanted to start with a puzzle that's been around for a long time, but it was brought up again about a year ago or 2 years ago, I'm forgetting, by a nice paper by Douglas Sanford and Zhenbin Yang. And this is the question of what happens if you jump into a typical state black hole. So a black hole in a typical state. So to form a typical state, you can start with a black hole at time 0, and you throw in a particle, let's say from the left, and you let the particle fall in and let the black hole thermalize. And as time goes on, the black hole will approach typicality. That's the expectation from chaos. And after a very, very long time, a time of order e to the black hole entropy, if you jump in, let's say from the right, you expect to not see anything. So at this time, the black hole will become, yeah. Just because that's when you've cycled through enough states to fill the black hole Hilbert space. Yeah, thanks. So the black hole will be well described by a typical draw from let's say the Haar random ensemble. At that point, well, not quite the Haar random ensemble, but something like that. But here in this picture, if you jump in, it looks like you don't see anything. You miss the excitation. You just hit the singularity, and nothing happens to you when you cross the horizon. But there's another way to form. So I should say this is what we call the black hole phase of the thermofield double, because you're jumping in when the length of the black hole is expanding, or the volume of the slice is expanding, and that's sort of the reason why you miss this excitation. But another way to form a typical state would have been to drop the particle in on the left and then evolve very, very far into the past, again by an amount of order e to the s black hole. But this time when you jump in from the right, you see a really huge shock. So it seems like there are two ways of forming a typical state, and they give you completely contradictory answers. So the puzzle is just, yeah, so if we had jumped in the past, we'd see this huge collision. And this is the white hole, what we call the white hole phase. Here, the length of this slice, or the volume of this slice, is decreasing as when you jump in. And that decrease is the reason that you get some boost, and you see a huge collision. Okay, so the puzzle is just what's the answer? What do you see? And in particular, what's happening here is that typical states sort of have a symmetry, where if you act on a typical state by unitary, it sort of leaves the ensemble invariant. And so it shouldn't really matter whether you had evolved very far in the past or very far in the future. You should get roughly the same description for the state. So there's a symmetry here, sort of a time reversal symmetry, that seems to be not respected by the semi-classical picture of the black hole. And what Stanford and Yang proposed is that at very late times, this symmetry can be restored via the emission of baby universes due to space-time wormholes. So these are exactly the same type of space-time wormholes that have showed up all over the place in the last 6 years or so, 5 years. And they can be understood as sort of instanton corrections that correspond to the emission of a baby universe. And what happens to this black hole, what Sanford and Yang showed, is that what happens to this black hole phase when it emits a baby universe is it can tunnel into a white hole. And what they found was that at very late times, the probability amplitude for this emission to happen is increasing linearly with time. So when you get to times of order e to the s, because it's emitting a baby universe, it has some exponential suppression, but that can be overcome by the very long times that you're going to. Okay, so this is like a very beautiful idea, I think. And it would be wonderful if it were true, I think. But what it's really getting at is just, okay, what do you observe? And what Stanford and Yang wanted to do was take this picture and try to compute probabilities. They wanted a probability distribution for seeing, say, a shock or not seeing a shock when you fall into this black hole. And key to this approach is that you need some method of assigning probabilities. This is a difficult subject and has been around since the beginning, since the firewall problem came up. But in this talk, I'm going to do the most naive undergrad quantum mechanics thing and just apply Born's rule to non-perturbatively well-defined linear operators. And my big disclaimer is that I personally am not convinced this is the right thing to do for describing the experience of an infalling observer, but I'm going to do it anyway as an exploration of what you can do. Okay, but I'm also bringing this up as a point of discussion for this conference. I think this is one of the biggest outstanding problems in understanding black holes, and I don't think we know what the answer is. So yeah, we need to figure it out. Yeah. I'm exploring what happens if they do, and I'm not convinced that their experience is described by linear observables on the boundary, for many reasons that have been discussed over the years. Yeah, I don't know. Yeah. Sorry.
If the goal is to understand what an observer would actually measure, why are you considering an eternal black hole and not something that formed from collapse?
That's a good question. I think the belief is that the answers, the formalism and the answers that we get here should be easily portable over to, say, a black hole that's formed from collapse.
But there you don't have the time reversal symmetry, but
sorry,
still...
I should also mention that if you have in mind, say, like a flat space black hole, that doesn't, there you can't form a typical state, right? Because the black hole will evaporate, so it doesn't live long enough. So here, to really get this paradox, you need to set up something that lives forever, or for a very, very long time. So you could form a single-sided black hole from collapse and then let it sit for a very long time in ADS, in a box. But I don't think the answers there will be much different from the ones I'm getting.
Okay, thank you.
Yeah. And this is also simple, and that's hard. Just computation. Okay. Okay, so to compute probabilities, we need a notion, using Born's rule, we need a notion of a Hilbert space, we need wave functions, and importantly, we need an inner product. So we need to be able to compute overlaps of states. And often what we do in this universe of ideas around the gravitational path integral is we use the gravitational path integral to compute these overlaps. And what has, you know, just the way you compute overlaps using a gravitational path integral, I shouldn't have to say this probably, but let me say it. You insert boundaries into the gravitational path integral that correspond to your states. So states correspond to boundary conditions in the path integral, and then their inner products just correspond to summing up geometries that end on those boundaries, okay? And what we've learned in the last few years is that higher topologies, space-time wormholes, can modify this overlap between states by a non-perturbatively small amount, by an amount that's exponentially small in the black hole entropy. So you could have between these two states, say, a handle. A perspective on this, it's not the unique perspective, but the way of formalizing, of thinking about this at least, is that this is a non-perturbative change to the inner product of the theory. So in other words, you keep the vector space, the background vector space fixed, so it's the one given to you by semi-classical physics, but the inner product gets modified, and so you get a new Hilbert space. So you have your perturbative inner product on the left, which I'll denote with the subscript 0, and then the non-perturbative inner product on the right, which is the exact thing that includes all higher topologies when you do the sum over geometries. And sort of the important point, or the key point, the key point, is that this non-perturbative inner product has null states. So to get a good Hilbert space, you have to mod out by these null states, and that reduces drastically the dimension of your Hilbert space. So you might start with something, as I'll show, that has a, let's say, a very large dimension. You could go from, well, let me just say that. Very large dimension to a smaller dimension, yeah.
Setup that you had, which on the left side. So there's a small operator on the left side. Wouldn't it have to be somehow engineered as some kind of complicated thing from if you just had a single-sided perspective and you're genuinely talking about typical states?
You mean if you just wanted to form a typical state not by some time evolution or something?
No, I'm saying that if you had a single-sided CFT and you're looking for typical states in it.
Yes.
So the candidate for the probe that you put in from the left side would have to be engineered from the right in some complicated way.
Yes,
right?
yes.
So in which case, is it clear that the symmetry that you're talking about is actually there between the time advancing on one side versus time advancing on the other side?
Sorry, when I'm talking about time going forward, I mean a two-sided time.
Right, that's right.
So going forward on both sides or going backwards on both sides.
That's right. So, but I'm saying that, like, ultimately you would be, I presume that, like, when you talk about a typical state, you would really be interested in a typical state in one CFT, right? And so there, the left insertion, like, I think there is a breaking in the symmetry in the sense of, like, like this left insertion has to be engineered somehow from the right operators, right? And in that sense,
it's not clear to me why it has to be engineered from the right operators. Can't I just, I'm talking about a typical state in the, let's say, in the Hilbert space.
So in the two-sided Hilbert space, I agree with you that there is a symmetry.
Yes.
But
yes,
my question is that if you really wanted to formulate this for a genuine heavy state in the holographic CFT, which is a microstate for the black hole, you would, the left-sided insertion would have to be engineered in terms of operators in the right, in the one-sided CFT, right? I mean, this question will have to be formulated in a way so that there is a contradiction.
It's not clear to me that it has to be, that you do need to do that to form a contradiction. But
but you mean from the, maybe from the 2D, from the two-sided the place, I think, there is, but I think it's also a less interesting question in some sense, right? So if you wanted to find a genuine contradiction, I would imagine that you have to find a similar statement for a typical state in a single-sided CFT.
Yeah, that's not clear to me.
Okay.
Maybe we can discuss that after.
Thanks.
Yeah.
Maybe the symmetry is like a future past symmetry, not a left-right symmetry.
Yes. Yes.
The 50-50 was future versus past.
Yes. Yes.
So, but even then, I think that the light operator and the left operator, they are not of the same type, right?
That's the same in future and past.
They are the same, but maybe we can discuss, because I think that the insertions are not the same is what I'm bothered by. So on one side, it looks like a light operator, and the other side, it seems like a complicated operator. So anyway, I think we can,
Maybe let's talk offline. Sorry. Okay. So are there any questions about this perspective that I'm taking here? So the goal of this talk will just be to analyze this perspective, specifically in this case of JT gravity. So just to review rapidly, JT gravity is a theory of two-dimensional dilettante gravity. It's a theory where the metric gets localized to constant negative curvature metrics, sort of the simplest 2D dilettante gravity in some sense. And one way of analyzing this theory is from a canonical perspective, where you start with the classical solutions of the theory. So this was done by Harlow and Jaffrus. And it can be described in terms of a two-dimensional phase space classically. So a good coordinate on this phase space is this length of a geodesic that connects two boundary times. And you can find the symplectic form in terms of, you can find the Hamiltonian in terms of this length and its conjugate. And you get this Liouville quantum mechanics. This was shown by Harlow and Jaffrus. And the wave functions for this guy are known. Doesn't matter what they are for the purpose of this talk, but they're known. And they have some completeness relation where they're delta function plane wave normalized. And they have some density of states here, which is this famous cinch density of states, which sort of gives you the completeness in the energy basis. So you can transform to fixed energy, and you get this density of states. Okay, but there's another perspective, which is sort of the perspective from the path integral, where you define, as I was saying, states as boundary conditions in the path integral, right? So now this boundary is labeled by a geodesic, so extrinsic curvature equals 0 slice of length L. And to find overlaps, again, we would just sum over all geometries with that as a boundary condition. Another interesting class of states are the ones that are more relevant in holography, which are these asymptotically defined states, where they're defined in terms of, say, boundaries, asymptotic boundaries of some renormalized length tau. So these are like thermal states, Hartle-Hawking state. And you just compute these overlaps by summing over all geometries. And at the disk level, this overlap was computed by Zhenbin Yang in 2018, actually before Harlow and Jeffers. And they found exactly what you would get if you had, or Zhenbin or Harlow and Jeffers found exactly what you would get from the canonical picture, which is just you expand the state in the energy eigenbasis and evolve for some complex time tau. Okay, so these two pictures agree at the perturbative level. And our perturbative inner product is just this delta function. But non-perturbatively, these states L, which again are just defined by boundary conditions in the path integral, are overcomplete. So one way to see that is let's say I want to take the norm of some state beta, and I try to put in the resolution of the identity in this L basis. At higher genus, I'll have handles, and when I insert this ket L bra L, that's like inserting two boundaries, each of length L. So what I do is I take a given geometry and I cut it along a geodesic, and then I sum over all possible geodesics. That's that integral over dl. But the problem is that at higher genus, for given two boundary points, you have an infinite number of geodesics connecting the same two boundary points. So one way to see this is you have one that cuts through the handles, one that goes around the handles, and then you'll have winding geodesics that sort of go in between the two handles and back out, and they can wind an infinite number of times, or an arbitrary number of times. So you get this infinity here. So this is telling you something that this L basis is non-perturbatively overcomplete. Okay, so how do we deal with this? Well, in this paper, we dealt with it by leveraging a property that's special to JT gravity. And that property is that for a given boundary segment, or a given boundary, for a given boundary segment in any geometry, there's a unique geodesic that's homotopic to that boundary segment. So no matter what garbage is happening in the middle, you can always find a unique geodesic that sort of avoids all the garbage and is homotopic to your boundary region, or is, yeah. So by doing this, we can take a given geometry and divide it up into, so let's say a given geometry which is computing the overlap of two boundary states, we can divide it up into three regions. One region is this exterior here, which is homotopic, which is bounded by the geodesic, which is homotopic to that boundary region. One region here, which is the same. And then all the geometry, all the non-trivial topology is bounded by these two geodesics here. Yeah.
By gluing these two geometries along this geodesic of length L, now, I mean, why can't you just now forget the fact that there was a geodesic and get this disk topology and do the integral over that topology along with handles?
Because, sorry. So you could forget about the geodesic and do the integral over
It's
the
specified by the
geometry with handles.
topology of the boundary. Yeah.
But you have to be careful about the mapping class group, and that which makes computing, like, say, the moduli space volumes for these geometries quite complicated. Mm-hmm. And that's precisely related to this issue of overcounting the geometries when you divide the geometry up along geodesics, because these winding geodesics are related via the mapping class group. So the goal here is to cut up the geometry so we can avoid, so we can define states.
So is there another way of saying this? Is it that the mapping integral over the moduli space ends up being divergent?
No. The integral over the moduli space is finite.
Okay.
But if you wanted to form these geometries by cutting it up and then gluing it back together, you would need to worry about overcounting the geometry an infinite number of times to get the right answer. So you need to divide by an infinity to get the moduli space answer. The reason I want to cut up the geometry is because I want to associate states and compute wave functions and so on and so forth.
But I was thinking that once you compute the inner product by gluing, now you just think of that as a path integral.
But so let's say I glue this.
Yeah.
Let's say I glue these two, or let me go back. Let's say I glue this, and now I sum over L. When I do that sum over L, it will also include this geodesic in the sum. So I'll overcount this geometry by every time there's a geodesic.
Okay, thanks.
Yeah, that's an important point. So, okay. Oh god. So so I've divided the geometry up into 3 regions. One is this exterior region, which has no topology. 2 of them are these exterior regions have no topology. One is this interior region. And I'm going to interpret this as these exterior geometries compute coefficients of the vectors in your background vector space. And then this eta of LL prime is just your non-perturbative inner product, because this is the thing. This is precisely the thing that has all the topology in it, and it's bounded by 2 boundaries of which are geodesics of length L and L prime. So it's precisely the non-perturbative inner product. Yeah.
The left-hand side of this equation is the non-perturbative left beta and beta prime.
Yeah. Sorry, these should be beta and beta prime. Sorry. Yeah. Okay. So So the non-perturbative inner product is just this thing where you take L and L prime and you sum over everything. This X is just everything in the middle, and that's precisely what I inserted here. Okay. So the length inner product has been modified non-perturbatively, and we can actually describe. Let me just. We can describe what this length inner product is. Sort of at all orders in the genus expansion by remembering that JT gravity is actually a matrix model due to Stanford. And the idea is that what's happening is that this length inner product, you should think of it as an observable that can be computed in the matrix model. So it's some operator that you can insert into your matrix model and integrate over different matrices. So different Hamiltonians of your boundary theory will give you different inner products. In particular, you could compute the averaged inner product, where that's just the thing that I've been discussing so far, where I sum over all possible topologies in between L and L prime. So at leading order, I just get nothing. That's the delta function. Then I get, say, a handle, 2 handles, so on and so forth. And what you can do is argue, what we argued is that because of these completeness relations for these phi e of L's, and because those wave functions in the background vector space don't get modified non-perturbatively by construction, you can actually show that this inner product, all that happens is that, you can write this overlap using the density of states. Remember, I showed that completeness formula. All that happens is when you include these genus corrections, it just modifies the density of states, but it leaves the vector, the wave functions unchanged. They're still the perturbative wave functions, but the density of states gets modified. So this is a non-perturbative completion of this overlap. So you just get the average of rho here. So but it's including all sort of higher loop corrections in the matrix model. And in particular, you can do the same argument. If you have many of these inner products, just like you could have many partition functions in JT gravity, you can insert many inner products, and they can be connected. So each of these is an inner product of L1 and L1 prime, say, or LK and LK prime. And they can be connected by various topologies. And by the same arguments, this uses this fact that the a given boundary segment is only homotopic to a single geodesic. That all that happens is that you just modify you just compute the correlation of the density of states, but you just multiply out by these wave functions. So in other words, topology just modifies the density of states. So from this, we can conclude that actually this non-perturbative inner product is just exactly equal to the density times these wave functions. So it's really just, so in a single member of the ensemble, it just projects down to a sum over the energies of these wave functions, basically. So when you're in a single member of the ensemble, you project down to a discrete spectrum, let's say, and the non-perturbative inner product is just this sum over products of wave functions. This is very reminiscent of this work by Shreya and her co-authors, where they argue that the black hole Hilbert space, or the semi-classical Hilbert space, is embedded into the non-perturbative Hilbert space non-isometrically. So here you're sort of seeing that explicitly. So the non-perturbative inner product is just like the perturbative inner product, except you just project down onto energy eigenvalues that are in the exact spectrum. So using that formula, it's easy to write down these null states that I mentioned that are so important. You could almost guess based on what I said. It's to write them down, it's convenient to do some Fourier transform to energy basis wave functions. And then the non-perturbative inner product of some general state here is just its sum over the Fourier coefficients in the energy basis, but only the energies that are actually in the spectrum, only including the energies that are actually in the spectrum. So all the null states are the ones that are just not included in the spectrum. Just project those out. Okay, so that's the Hilbert space and the non-perturbative inner product. And now you can talk about observables in this theory. And so,
Sorry,
yes.
naively, there was a continuum of energies.
Yes.
And you're projecting down to some.
Yeah, it's very strange. Yeah, I agree. Yeah, but that's what's happening. Yeah. Yeah, so we can show that this non-perturbative inner product, we can compute all of its moments in the matrix model, and they agree with this function at all orders in the matrix model. Now, there's some question about whether that means they still agree non-perturbatively in the matrix model, but
sorry, I mean, the South-Shankar-Stanford matrix model, at least in the double scale limit, has a continuum of energy.
Yes, yes. I'm saying now, so this inner product is an operator in the matrix model. So it has a value for every matrix that you integrate over in the matrix model. So now I'm saying pick one of those matrices, that's your Hamiltonian. This will be the value of that observable. It's like saying Z of beta is an operator in the matrix model for a given. Sorry, where's the choice? It's been made by you. I mean, or by you picked a random Hamiltonian. I mean, here we really have an ensemble, so it hasn't. Sorry, here sorry, my notation is maybe a bit confusing. It's important here that I have an overbar, which means an averaging over the matrix model. So it's something it's an expectation value, let's say, in the matrix model. These would be like correlation functions of this correlation numbers of this inner product. And now I'm back to an operator. I should have said this. I'm thinking of now as an operator in the matrix model. And now if I restrict to a single matrix that's one member of this ensemble, it'll take this form. So I tried to argue that this LL prime inner product can be rewritten in the energy eigenbasis. And when you do that, the wave functions that you integrate the density of states against don't change. The only thing that changes is the density of states. It gets corrections from the genus expansion. And so the average in the ensemble of this inner product is just the average of the density in the ensemble times the wave functions. Furthermore, for the correlation functions, it's just the correlation functions of the densities times these perturbative wave functions. And so if you know all the moments, you know the operator, is what I'm trying to say. Correct. Yeah.
Sorry, so I didn't fully understand.
Well, I have some random variable, and I've computed all its moments, and it agrees with some other random variable in all its moments. Yeah, so I'm saying there.
What is the argument that that this wave function doesn't change?
Yeah, that's just this fact that in JT gravity, I can find this unique slice, which is homotopic to the boundary. So I can always just put all of the topology in the interior, and the wave function is just computed by the perturbative wave function. Okay. Yes. Yeah, all I mean by that is that as an operator in the matrix, as an observable that you can insert into your matrix model, this observable is equal to, let's say, the density of states times these wave functions. Or really, I should say it's these wave functions evaluated at the Hamiltonian. So that's an operator, it's a function of the Hamiltonian, and it's some operator you could insert into the matrix model. And then for a specific Hamiltonian, it reduces to this thing.
Where this, ensemble, you were, trying to come up with an ensemble which explains some semi-classical results, right? And now you have that, and now you want to go back and try to find some more microscopic type of description. And from that point of view, if you want to explain higher and higher movements, you would just keep on modifying your ensemble. But here you are taking the point of view that you want them to match all of the movements. So the ensemble, I mean, then it has to match member by member.
Yeah, although I'm not, so the ensemble here is fixed. I'm just discussing different observables you could compute in that ensemble.
Okay. Thanks.
If that makes sense.
So I thought that normally if you do non-perturbative completions of these matrix integrals, they're ambiguous, but you have to choose a suitable complex contour and so on.
Yeah.
I thought that none of those non-perturbative completions was equal to a single draw from the matrix model.
Yeah.
So to what extent is this a bona fide non-perturbative completion of the matrix integral?
I'm not finding a non-perturbative completion of the matrix integral. I'm just saying that this inner product, okay, the full content of my statement is that this inner product, viewed as an observable in the matrix model, has the same moments as some other thing, which is just this operator as a function of the Hamiltonian. It has the same moments to all orders in the genus expansion. So that's the content of my statement. Now we can, so I'm writing this suggestively as saying probably they're equal exactly for each member of the ensemble, but yeah, there are questions about non-perturbative effects in the matrix model that we comment on it, but yeah, it's not totally satisfactory. Sorry. Okay. Okay, so yeah, I'm not doing great on time, so let me just, I would just like to discuss operators in this theory. So I've discussed the Hilbert space. Now operators, I just can think of as general superpositions of a ket and a bra. Yeah,
sorry,
yes, go for it.
So one of the outputs of this is that there are a zillion non-perturbative completions, right, for each choice of the
well, that wasn't our work. I would say maybe that's in this SSS work, right?
But is that what you agree with? That Gravity is highly non-unique.
For JT gravity, I don't think this is, I think we expect this to not be true in higher dimensions.
I think we should discuss it. I thought what came out of SSS was that gravity is the random average over the double-scaled matrix theory.
Yes, observables in gravity are computed by correlators of observables in, let's say, random matrix theory.
So
yes.
that's an average over various.
Yeah. That's all. That's the only. I'm not modifying that statement at all. This is consistent.
Aren't you claiming that each choice of the matrix is a non-perturbative completion
of gravity? Insofar as Shankar-Sanford would say that.
Is this what you are saying?
No, I'm not. No, I don't. I mean, at least in the JT gravity case, perhaps. Yeah.
So if you could go back to your previous transparency. No, the one with the non-perturbative inner product. The word's non-perturbative on it. Yeah. Sorry, maybe I'm completely misunderstanding. No. But I thought that was, you had one of these non-perturbative inner products associated with each choice of a matrix. Because you've got a spectrum and so on.
Yes.
So then there are a zillion different non-perturbative completions.
In this toy model, yes. I should say this is all up to these issues that Jan brought up, which is that there are issues about defining the matrix model doubly non-perturbatively in the black hole entropy.
I'm not talking about what's correct. I'm just asking what you're saying.
Okay. Yes. According to this slide, that's what I'm saying. Yes. That's
which matrix you picked, and its average is the second number. This row of E, right? You just averaged over the whole thing.
Well, sorry, I have in mind these as not as averages, but as exact statements. So like this row here is a sum of delta functions, let's say.
But what's the content of the second equalities? I think that is what is confusing.
Nothing, I just plugged this in. Sorry. What I should have written here, you're right, is that it's a function of the Hamiltonian. So
those are not literally equal, right? Those second and third things.
The trace. Subscript in your head to the thing on the left. Sorry, what I should have written here was on the right. It should have said trace over the Hilbert space of phi h of L, phi h of L prime, where this is some function of the h operator. Does that make sense? That's what I should have written. No, this is an operator, just like e to the minus beta h trace is an operator that I could insert into my matrix model. This is another operator I can insert to my matrix model. And the claim is that it computes this inner product. Yeah, sorry. Depends on H. Yeah, thank you, John. Thank you. Yeah, thank you. Sorry. Okay. Yes. Let's say. Yeah, yes. We don't. We're not addressing that. We're not trying to address that. No. But that's viewed as in this picture. That's viewed as as an integral over different Hamiltonians. So that's an average or a correlation function of, let's say, inner products. So I could compute, say, the two-point function of L prime, and that would have a trumpet-like geometry. So I could compute the average L prime, L double prime, L triple prime, averaged over all choices of this Hamiltonian. And that would be given by something which has a geometry. Right, but in that case, for a given instance of the Hamiltonian, we don't know what the geometric picture is. So I'm just stating this, I'm just stating this as a statement about equivalence of operators in the matrix model.
What you mean is the next.
Yes, perhaps this would help, this one?
No, the one with the blue things and the, yeah, I mean, in that here, what
Yes.
you're writing on the left-hand side is what gravity.
Correct.
And
Averages.
This is some random
Correct.
matrix theory.
Correct.
Right?
Correct. But I could have thought of computing this thing on the left as inserting something into the matrix model and computing, say, correlation functions of that thing. And I'm finding that thing. Is that? Okay. Yikes. Okay, let me just say operators. So operators have a ket and a bra. Those correspond to inserting two boundaries in the path integral. And what you see is that when you modify the non-perturbative inner product away from the perturbative answer, there are an infinite number of functions, of operators that agree with the perturbative answer but disagree non-perturbatively. So let's think about the length operator. This should just be like integral over L, ket L, bra L, perturbatively. But now I could take any invertible function, f, and if I compute this thing, when L and L prime are diagonal or orthogonal, this just comes through and kills the f, and you just get the perturbative length operator. But if they're not orthogonal, you get some off-diagonal contributions to this operator, and it disagrees now. So for any invertible function, you get a different operator that agrees manifestly at the perturbative level. You might say that this f is like a choice of a non-perturbative dressing or something. So, but what is this operator geometrically? Well, let's compute the f of LF operator, which just sums over ket L bra L time weighted by this f of L. And this just inserts two boundaries in the path integral, and then sums over all two boundaries of length L in the path integral, and then sums over all geodesics weighted by f of their length, okay? Oh, sorry, this got cut off. So given a length operator, you can define this speed operator, which is like the derivative in time of this length operator. And this is what I was saying at the beginning is related to whether or not you expect to see a collision, right? When you're in the white hole phase, the length is decreasing. When you're in the black hole phase, it's increasing. So whether or not this operator is positive or negative tells you something about what you might expect to see. And in the time-evolved thermal field double, this operator for general F will be well localized around the semi-classical value, plus or minus 1 in some units, up to exponentially long times. One natural choice is, okay, in this paper, we just picked we examined some choice of F. That's a natural one. The reason this is a nice one is just because we actually can compute, using those Bessel perturbative wave functions, we can compute exactly its matrix elements. And we know what they are non-perturbatively. And then you can actually just draw numerically from an ensemble of matrices that has the JT spectrum. It's not totally obvious how to do that, but we know how to do that. And then you can try and compute the probability distribution of the length and the speed in these how do I get it to work? Oh no. Hang on. Compute the probability distribution of the length and the speed. Okay. Cannot play media. Okay. Well, if you want to see it, basically what happens is this is the probability distribution of the length. It's a well-peaked sort of Gaussian-looking thing. It travels out, and then it spreads, and then completely delocalizes at times of order to the s. Here, this is the probability distribution for the speed operator. It starts out well localized around +1 as you evolve in time, and then it delocalizes, and you can compute a time-averaged form of this probability distribution. And it has peaks around this semi-classical value, but at very long times, it also has a peak around this white hole value. So this is after times of order e to the s. You can also look at its probability distribution of eigenvalues. This is just showing why we actually saw some peak here. Since I'm totally out of time, let me stop there. And yeah, thanks.
Maybe one quick question before tea.
So just to maybe finish the loop on this H hat. So now you put a H hat on the first element of your three things. You have an H hat on the third guy, but where's the H hat on the second object?
Where's the H hat on, which is the second object?
The second object was this integral dE rho E.
Sorry, all I meant by that was expand this out. This is equal to integral dE, rho of E, phi E of L prime.
Rho E is just a sum of delta functions. It's not a sinh right now.
Correct. That's what I wrote underneath.
So this rho is dependent on H hat.
Correct. Sorry, yes, this rho is dependent on H hat. Sorry, thank you.
Yeah. Just quickly, can this computation be done in the Virasoro minimal string? And is there anything to be learned if it can be done?
That's an interesting question. Probably. Yeah, I mean, a related question is about, so you can think of the Virasoro minimal string as another dilettante gravity, and another question is about whether these results hold for more general dilettante gravities. It's an interesting question. I'm not sure. But yeah.
Okay, in view of time, let's thank Adam again.